Hello and welcome. In today's video, we were going to explore an interesting way in solving mazes using Tremaux algorithm. Yes, you've heard it right. Sounds complex? Don't worry, because we were going to break it down and explain to you how this algorithm helps us to navigate through mazes and unfamiliar spaces. Let's go!
What is Tremaux' algorithm? Let's start with a question. What do you do when you find yourself in a maze or an unfamiliar place? You don't have a map, you don't know the layout, and you just want to get out. This is where Tremaux' algorithm comes in. It's a way of systematically solving mazes by marking paths as we go, so we don't get stuck in loops and dead ends. Imagine walking through a maze, and as you explore, you mark each path you take. If you reach a dead end, you backtrack and try another way. The algorithm ensures that you won't go in circles and you won't miss any possible routes. Tremaux' algorithm was created by French engineer Charles-Pierre Tremaux in the 19th century as a simple and reliable way to solve mazes by marking paths to avoid unnecessary retracing. Unlike the wall follower, which can fail in complex mazes, Tremaux' method guarantees full exploration without repetition. It's related to search algorithms like DFS and BFS, but uses path marking to reduce overhead. Later techniques like A and Dijkstra's added heuristics for finding optimal routes. The Tremaux approach laid the groundwork for efficient and complete maze-solving methods still used in robotics and AI today.
Now, let's dive into how the algorithm works. The idea is simple. At every junction or intersection in a maze, you make a decision about which path to take. If you've never been down that path, you walk down it and mark it. If you've already been down it, you keep moving. If you reach a dead end, you turn around and try another route. This approach is great because it helps you explore every possible route, and if you get stuck, you just backtrack to a previous junction and try another path. You won't miss any dead ends and you won't waste time tracing your steps.
So why Tremaux' algorithm useful in real life? Well, imagine you are in a public building or spaces or even on a forest and you need to find your way out. Without a map, you'd rely on something like Tremaux' algorithm to explore the area systematically.
Now, let's talk about the time it takes for this algorithm to work. This is called the time complexity, which basically means how much work the algorithm has to do to solve the problem. Tremaux' algorithm operates with a time complexity of O times V plus E, where V is the number of junctions or decision points and E is the number of corridors or connecting paths. The algorithm works by marking each path it takes. A corridor is traversed at most twice, once when moving forward to explore and possibly again when backtracking from a dead end. This means the total number of path traversals is bounded by 2 times E. Junctions are only evaluated when a decision is needed, so the total number of decision steps is directly proportional to V. Altogether, this gives us a total operation count of V plus 2E, which simplifies to O times V plus E in terms of time complexity. This linear growth means the algorithm scales efficiently with the size of the maze. In practice, this ensures that each path or edge is used efficiently. Each junction or the vertex contributes only when necessary, and no unnecessary steps are taken. As a result, Tremaux' algorithm guarantees complete exploration of the maze with minimal redundancy, making it both systematic and computationally efficient.
Imagine a rescue robot entering a collapsed building after an earthquake. The layout is unknown and dangerous, with many blocked paths. Using Tremaux algorithm, the robot can systematically explore the environment, marking where it has been, and carefully avoiding revisiting dead ends unnecessarily. This methodical exploration helps the robot efficiently map the space while minimizing wasted movements, which is crucial when time and battery life are limited.
Different environments presents unique challenges. For instance, a maze with many loops might cause other algorithms to get stuck revisiting paths. Tremaux' algorithm handle this by marking and recognizing paths already taken, which prevents endless loops. However, in very large or weighted mazes, this algorithm doesn't prioritize the shortest path, which can increase exploration time.
Welcome to another Tremaux algorithm maze simulation. Let's walk through how our JavaScript code works behind the scenes. We start with the start Tremaux function, which initializes everything needed for solving the maze. First, we call create maze. This draws the maze grid on screen, setting up walls and paths visually. Next, we reset important variables. We clear the stack, which keeps the track of our path. We also reset marks, which records how many times each cell has been visited. Then, we set our agent at the starting point, which is the top left corner, at position 0 and 0. Finally, we push the starting point onto the stack to begin traversal. Now, let's go into the maze traversal loop. We use a while loop that runs as long as there are positions to explore in the stack. Inside this loop, first, we look at the most recent cell in the stack and move the agent there. Second, we update the display to show the agent's new position. Then, we pause for 300 milliseconds to animate the movement. We immediately check if the agent has reached the goal. If it has, we stop and show an alert that the goal has been reached. Otherwise, we mark the current cell as visited. We also initialize a move variable to false, which will help us track if the agent finds a new path to move. Then, we define the possible directions the agent can move: up, right, down, and left. For each direction, we calculate the next possible cell. We check if it's valid, meaning it's within the maze and not a wall. If it's valid and either unvisited or visited only once, we add it to the stop. Mark move as true and break out of the loop to explore this new cell next. If none of the directions lead to a valid move, we backtrack by removing the last cell from the stack. This backtracking ensures that the agent doesn't go in circles and revisit only when necessary, just like how Tremaux' algorithm works in real mazes. Finally, if the loop ends and the agent hasn't reached the goal, we display an alert saying the maze was fully explored, but the goal wasn't found.
Now, let me show you another simulation. This simulation demonstrates how Tremaux algorithm works in practice. Built using HTML, CSS, and JavaScript, the code creates a maze environment and places an agent at the starting point. The agent follows Tremaux' rule to navigate, marking visited paths, avoiding loops, and backtracking when necessary. When the simulation is run multiple times, an interesting pattern emerges. is actually a key insight into how Tremaux algorithm operates. The algorithm doesn't follow a preset route. Instead, it makes decisions based on available unvisited paths at each junction. In each of the 3 recorded runs, the agent takes a different path through the same maze. This might raise a natural question. Why does the route change, even though the algorithm remains the same? If more than one valid direction exists, the choice can vary depending on the order directions checked, such as up, right, down, or left. As a result, the agent may explore a different path on each run, even though the logical process stays consistent. This controlled variation is not a flaw, but a feature of Tremaux algorithm. It shows that the method is robust and adaptable. No matter the path taken, the algorithm ensures that all paths are explored efficiently, dead ends are avoided, and the maze is ultimately solved. This approach is especially valuable when complete exploration is more important than speed, like search and rescue, robot vacuum cleaning, or network troubleshooting. In these cases, ensuring every accessible area is covered outweighs finding the shortest route. But when speed matters, other algorithms like A-star or Dijkstra's, which use heuristics to find optimal paths, are preferred.
Let's quickly compare Tremaux' algorithm to random walk and depth first search. Random walks can waste time going in circles without memory, while DFS might get stuck exploring deep paths that don't lead to an exit. Tremaux' algorithm balances exploration with path memory, avoiding redundancy and ensuring all routes are considered. However, it doesn't optimize for path length, unlike heuristic-based methods.
Let's delve into a comparative analysis of Tremaux' algorithm alongside 2 other popular maze-solving strategies, depth first search and the random walk algorithm. This evaluation highlights their execution times and overall efficiency when applied to mazes of increasing complexity. In relatively simple mazes containing 1,000 paths, DFS proved to be the fastest, completing the maze in just 0.6 seconds. Tremaux' algorithm followed closely behind with a time of 0.9 seconds, while the random walk method lagged significantly, taking 2.8 seconds to finish. As maze complexity increased to 5,000 paths, DFS continued to lead with a completion time of 2.9 seconds, while Tremaux' algorithm performance scaled proportionally, solving the maze in 3.5 seconds. Random walk, being inherently inefficient and unguided, took much longer, 13.6 seconds. In the most complex test cases involving mazes with 10,000 paths, DFS once again completed the task fastest at 6.4 seconds. Tremaux' algorithm managed to handle the increased complexity reasonably well, finishing in 7.8 seconds. However, random walk dramatically underperformed, taking 28.2 seconds to reach the goal. These results illustrate that while DFS is the fastest in ideal conditions, Tremaux' algorithm provides a balanced approach with reliable efficiency and structure, particularly when navigating unknown or dynamically generated mazes. In contrast, random walk lacks direction and predictability, making it the least efficient option, especially as maze complexity grows.
To summarize, Tremaux' algorithm is great for thorough exploration with minimal memory use, making it ideal for unknown or dynamic environments. But if your goal is to quickly find the shortest path, it may not be the best choice. Understanding this trades-off helps in choosing the right algorithm for the right task.
In conclusion, Tremaux' algorithm is a foundational tool for navigating unknown spaces methodically. Its simplicity and reliability make it useful in robotics, AI, and other fields where full exploration is necessary. Thanks for watching! If you want to explore more algorithms or have questions, drop a comment below and don't forget to like and subscribe for more insightful videos.